Welcome back.
Training neural networks with adaptive learning rate. Okay. Now, neural networks are trained using ERM. Via gradient descent. Now, if suppose r cap of theta is the empirical risk. Now, gradient descent estimates the parameters as follows. Now, you have theta t plus 1 to be theta t minus alpha times the gradient of the empirical risk with respect to theta. Right, this is what the first order gradient descent is all about. There are versions to it, right? One version is what is called as the stochastic gradient descent. Where compute r tilde of theta as estimate the loss on a set of samples, right, which is where B is a subset of the data set D randomly sampled. We already saw that, right? This has a regularization effect is what I told you. So this is called stochastic gradient descent or SGD, where if you have 1000 samples, you construct a batch of 32 samples or 64 samples, which is again a hyperparameter, and then perform the gradient descent. And one full walks through the entire training data is called an epoch during training. Okay. An iteration is where you do one forward pass and one backward pass through uh, the neural network that you are training. If you do a stochastic gradient descent and pass through the entire data set once, then it's called an epoch, and training is done for several epochs. That's how the training is done. Okay, this is stochastic gradient descent. Uh, but in both in stochastic gradient descent and gradient descent, right, the step size, okay, alpha is fixed. This is also called learning rate. This learning rate is fixed in stochastic gradient descent. You fix it to a particular value, okay, and you keep it the same. But in optimization, we know that while we are looking at gradient descent or rather numerical algorithms, we may have to take a larger step at times where the gradient has larger magnitude and you are near the optima. You have to take a smaller step at other times and so on. So basically, instead of having the fixed learning rate, it's always a better idea to have adaptive learning rate, the learning rate that adapts. Okay, so there are techniques that would incorporate this. There are a few adaptive learning rate techniques. For gradient descent. We look at uh, a few famous such things. The first thing is called SGD with momentum, where the idea is as follows: define momentum mt as beta 1 times m t minus 1 plus 1 minus beta 1 times gt, where so gt is the gradient of the loss function, and now you make theta t plus 1 as theta t minus some alpha times mt. Yeah, what is this doing? This mt is a running average of the gradients, moving average of the gradients. At t equal to 1, it is simply the gradient. Okay, at when you initialize mt m0 to 0, so it's equal to the gradient. As you keep moving in time, the m term will keep accumulating the gradients and taking an average of it as we move on. Okay. Now, instead of subtracting the gradients, you subtract the accumulated gradients over time. Why is this a good idea? So, you are computing the exponential decaying average of gradients, which means in earlier times you take larger steps depending upon the gradients, and the later steps you take smaller steps with the gradient, because the gradients are being accumulated over time. So, this is called SGD with momentum, and this term MT is called the momentum term. Okay. The see here what did we do is that we accumulated the gradients, but we know that in optimization the first order gradients are not enough, right? You need to accumulate the second order terms of the gradients as well. Why? Gives you the acceleration effect. Right? So, instead of only looking at the first order gradients, or rather the gradients, look at the gradient squared terms as well. Okay. So, this is called, this is another adaptive learning rate method, which is called RMS prop. So, here instead of averaging the gradient, you average the second order, or rather the square root of the gradient. Define Vt to be some beta 2 times Vt minus 1 plus 1 minus beta 2 times Gt squared. We are accumulating the square root of gradients here. Now, you make theta t plus 1 to be theta t minus some alpha divided by root of Vt into Gt. So, why do we need this root of Vt? Vt, the dimensions of the Vt, I mean not the dimensions, our dimensions, it is the physical dimensions of Gt is square root of gradients, right. So, root of Vt has the dimensions as that of gradients, and Gt is gradients. They both cancel, and the one that this will be of dimensions of the parameters, and that is why you can add and subtract them. The dimensionality has to match, right. Yeah. So, that is why this is the RMS prop, where what we are doing is that instead of using the first order gradients, or rather the gradients, we are using these gradient squared terms. Okay. Why do we have to do this? See, we are scaling the gradients. All gradients are now being scaled with a particular value. This particular value is inverse of their squared. So, the gradients, okay, are the parameters for which the gradients are damping, higher the gradients, they dampen quicker. The lower the gradient values, they dampen slower. So, here what we did was we dampened all the gradients no matter what their so called acceleration is. Here they are being scaled by the inverse of the damping factor or the acceleration, that is it. Okay. This is about RMS prop. The other update to this improvisation of this is what is called as adaptive momentum estimation. Also known as Adam. And by the way, even though I have written it this way, right, if theta are vectors, these are done at the element level, the parameter level. I mean, these things are actually the Hadamard products, because when you take the square root of gradient, you do it dimension wise. Each of the dimension has to be multiplied. So you please note that if you do this, then there is a different learning rate for different parameter also. You understand? There is adaptability across different parameters. You know, some parameters are updated faster or larger, and some parameters are changed slower, because this is happening at the parameter level, because these are vectors. No, we are looking at Hadamard products here. Do you see that? Okay. So this adaptive momentum estimation, which is referred to as ADAM, actually combines both. It's a combination of both the RMS prop and the SGD with momentum. There we have both the terms. So compute momentum as beta 1 times mt minus 1 plus 1 minus beta 1 times gt, and beta 2 times vt minus 1 plus 1 minus beta 2 times gt squared, and the final estimate theta t plus 1 is theta t minus alpha divided by root of vt times the momentum. So this is a combination of both the RMS prop and the momentum term. You have both the momentum and the second order term. This is called ADAM. Now if you go to the standard optimizers such as PyTorch, etc., you have the facility to choose your optimizer. You can choose SGD, you can choose RMS prop, you can choose SGD with momentum or ADAM. ADAM is the go-to choice for optimizers in today's learning, because empirically it has been observed to be leading to good better convergence. Now you have to choose this beta 1 and beta 2, they are hyperparameters. Okay, adaptive momentum estimation. Now that we are talking about optimizing neural networks, there is one point that I would make, which is better to be known. See, we are using gradient descent here, okay, to optimize over the parameter space that would be typically a very large size, right? I mean, today they are of billions of parameters, you know, they can be thousands of. So we are optimizing in a very large dimensional space, and the objective function that is being optimized is not a convex function of these parameters. The empirical risk that we are optimizing is no convex function. Okay, so first order gradient descent does not guarantee that you will go to the true optima. In fact, it can be that the likelihood of these methods taking you to the true minimizer is very low, and it can be shown mathematically. Let me just tell you that. So let us say that we are operating in a 1000 dimensional space. Our neural network has 1000 per 1000 is nothing. You know, a simple ant level MLP will also have more than 1000 parameters. Let us say that you have a neural network that has 1000 parameters. Now, suppose there is an optimization surface. When do you know, or how do you find out whether a given point on this optimization surface is a point of extrema or not? Recall your high school or college math. How gradient has to be 0, right? That will only tell you that the gradient vanishes at that point. How do you know that if it's a maxima or a minima? Second derivative test. You will have to always look at the second derivative test. Now, if you are working with vector valued functions, what is the equivalent of the second derivative test? Not the Hessian. Hessian is the equivalent to second derivative, but if a point has to be a global optima, then the signs of the eigenvalues of the Hessian matrix are all have to be of the same sign. If all of them are positive, or in other words, if the Hessian matrix is positive definite, then that particular point is a minima or maxima? Yeah, whatever, right? It has to be, it has to be, all the eigenvalues have to be of the exact same sign. Now, let's say that we are operating in a 1000 dimensional space. What is the size of the Hessian? Which is 10 raised to 6, a million. We are looking at a million uh, eigenvalues, looking at million eigenvalues. Let's say that we model the sign of the eigenvalue as a Bernoulli random variable with success probability P. What am I saying? With probability P, the sign of the eigenvalue of the Hessian matrix is positive. With probability 1 minus P, the success probability is the probability that the sign of the eigenvalue of the Hessian matrix is negative is 1 minus P. So now take this P to be 0.99999. So with a very high probability, the eigenvalue of this Hessian matrix is going to be positive. Now what is 0.99 to the power of 10 to the 6? No, 0.99 to the power of 10 to 6 is a very small number, right? Which means that the odds of any point that you land on the loss surface in a 1000 dimensional space being a global optima is extremely low. This with an assumption that the probability of it taking a positive value is 0.99. So what am I trying to say? So now we are looking at not at 1000 parameter neural networks, we are looking at millions and billions of parameters of neural networks. So almost always gradient descent will not take you to the point that is a global optima. Then what is the hope? The hope is, look at your validation data. The only question that we are, all the points that we land to with gradient descent are local optimas. The only question that is to be asked is your local optima better than my local optima? And how do we measure this? By looking at validation data. That's why when you train neural networks, there is no theoretical way to look at what the stopping criteria is. Okay, just you have, that is why people look at come up with benchmarks. You have test data, whatever neural network you train, perform its or rather extract its performance on test data, and that's your truth. That's it. Okay. In fact, there is one other nomenclature that is used. When you are doing gradient descent, right, every single point of gradient descent will give you a different model because you are navigating in the theta space, correct? And these things are called checkpoints, by the way. So what is shipped are checkpoints, model checkpoints. A model checkpoint is nothing but a particular set of theta for this architecture. So when you download a model, a pre-trained model from some of these commercially available libraries, Hugging Face for instance, what they actually give you are these thetas with an ERM done on a particular task. Start from it, either do inference on it or you can initialize another neural network with that and you do another ERM on top of it, or do distillation or do whatever you want. Is okay? So I think now we are in a position to take up a data set, take any neural network and train it for whatever task you want. This is the foundational principle of training any neural network for any task, including LLMs. And today's LLMs are trained on thousands of, or not thousands, hundreds of thousands of GPU cards for several tens of months on trillions of tokens of data. That's the scale. With billions of parameters, exactly. Right? That is what it is. Okay. Okay. So this completes our discussion on neural networks. We will next go to the classification and regression trees, decision trees, and subsequently we look at ensemble methods. Okay. Thank you.